The second part about the lecture on IT architecture is going to be the three different layers of architecture, and we'll talk about each part of IT architecture. Enterprise IT architecture is three layers. The first layer is the IT infrastructure architecture, and this is the digital plumbing of the firm used by all line functions and applications. This is usually a firm-wide arrangement and usually predominantly stable, a generic commodity, and is rarely a competitive differentiator. However, this can be a liability if it underperforms. This foundation usually consumes over 50% of the IT corporate budget. Constructing a transatlantic internet cable costs about $300 million, giving you a feel for how costly IT infrastructure can get. It must be reliable, but also economical, and this is a key choice for centralization. What are some of the non-IT contributions for this layer? One of the decisions which need to be made is how much to decentralize IT infrastructure, how much to centralize it. Centralization creates firm-wide economies of scale by aggregating IT infrastructure demands of all line function and eases analytics-friendly firm-wide integration, but also concentrates its vulnerability. Decentralization facilitates tailoring it to individual line functions, unique needs, but then increases the costs and because of duplication. And of course, there is a hybrid, which is a mixture. In theoretically, we can talk about centralization and decentralization in two different buckets. But in reality, you have a hybrid, which is a mixture of the two, which decentralizes some, but centralizes others, and therefore has the strengths and weaknesses of both. Generally, more centralized architecture is costlier to build, but cheaper to run than most decentralized ones. Commoditized infrastructure increases and not reduces opportunities for competitive advantage by freeing up more resources to invest in applications. The second layer is the application architecture. Applications are software programs that essentially give functionality to the hardware devices like PCs, smartphones, tablets, cash registers, other internet-connected devices, thermostat, camera, car systems, etc. Such devices, they're called clients, are used to access resources or services placed on more powerful central computer systems called servers. One server machine can serve multiple user devices which are connected through the internet. Now, application contains three building blocks of functionality, and these can be placed either centrally or individually. So here is user devices, and through the internet connects or through connect to the server. The three building blocks are interaction, functionality, which handles the app's interaction with users, such as receiving inputs, displaying outputs, application logic, which performs the core work and makes the application useful to its users, and finally data storage for data and application use. And application logic is where a lot of business innovation can be achieved. So it is possible to have the data stored in a centralized server. It is possible to have the application logic and the data in the server with only the interaction done on your device which you are holding. And a lot of times when you use an application which is used from a browser, that's what the browser is, the interaction area, and the application logic and data storage is done at the back end. And so there are different ways of setting this up. So we're going to look at 3 different arrangements of these app architecture. We talk about the cloud architecture, client-server architecture, and peer-to-peer architecture. Cloud architecture is more centralized and peer-to-peer is decentralized, and you can see this kind of moves in that particular region. The cloud architecture puts all 3 pieces on a central server. The user device is fairly simple, not very powerful, therefore inexpensive, because its only role is inputting and displaying information. So everything is in the central server, and you just have a window into the server's work. This is called cloud computing. Used to be called dump terminals when we were using mainframes, which you had dump terminals accessing a mainframe, and this was originally in the 1960s where you had mainframe dump terminals, and now you are moving back to that similar kind of paradigm. Each server could be expensive, of course, now compared to a 1960s or 1970s mainframe. A lot of these computers are far more powerful and a lot cheaper. So cloud architecture heavy lifting is done on the server side. Clients are cheap and feeble. Only input displays information, centralizes everything. There are advantages and disadvantages. Centralization generates economies of scale, eases maintenance issues. So you just have to upgrade the software on one side, not on individual devices. Reduces the need for in-house IT staff if other firm is managing the server side. Maintenance is easy because there's only one place where it needs to be maintained, upgrade, and bug fixed. New features can be constantly and instantly rolled out, unlike other application architectures where they are held until the next big version upgrade. But there are 2 weaknesses. Single point of vulnerability. So if someone wants to break in, does not have to break into individual devices, just one central server, and it needs strong, reliable internet connectivity, without which the application is useless. And here are the strengths and weaknesses of the cloud architecture. The client-server architecture is different. So we did move before, when we had the mainframe dumb terminal systems. In the 80s and 90s, we moved to this client-server architecture because there were some huge advantages from using it. And now we're moving back to the cloud architecture because we have better connectivity with the internet. We have much faster processors, and therefore we can use this. So here the interaction and application logic is in the client, and data storage is in the centralized, is in the central server. So it centralizes only the data. Clients do all the heavy lifting. This is very common in corporate portfolios, predates the cloud. It allows, there's a lot of potential for competitive differentiation because it's the it is in the application logic that you can perform a lot of the business differentiation. It can be costlier if it's custom built, if it's not off the shelf, but that's what gives a strategic advantage. It is burdensome to upgrade because you have to upgrade every machine, and if you have 5,000 machines, you've got to upgrade 5,000 machines. There are some newer cloud-inspired variants to enable cheaper, faster custom applications. So you have the service-oriented architecture where some of the server-side functionality can be purchased as a service and integrated into custom apps. and this essentially relieves the firm of some of the cost of custom developing and maintaining the application. The second part is microservices, which are discrete generic services that can be purchased from different firms to be assembled assemble the application logic of an app. An app built using them might integrate hundreds of microservices invoked through the internet alongside software code developed in-house. This can lower the upfront costs and accelerate the development of some custom apps. And finally, we are going to look at peer-to-peer architecture. Here we are using the ability, both the interaction, application logic, and data storage is in the client side user device, and we use the internet to connect multiple other devices to each other. There is no central server. Every user simultaneously also acts as a little server for other user devices. And the architecture draws its strength from essentially numbers. Every new user adds to the hive, increases collective capacity, potentially giving it infinite scalability. BBC, British Broadcasting Corporation, uses this kind of architecture to distribute video footage that did not make into the broadcast shows, which otherwise would be cost prohibitive to integrate. This is the difference between Facebook, which is a cloud architecture, and Skype, which is a peer-to-peer architecture, is clearly seen here. So is dirt cheap scalability a huge advantage, and that's why you can expand scalable. It's cheap, but however you have no control over user devices, which actually make it only useful in niche eclectic uses. This is why Netflix, which needs scalability, avoids it. And it's recommended only for scale-hungry applications that demand no control. So there's trade-offs in every architecture. No single architecture is optimal because every one of them have some benefits and some disadvantages. Non-IT managers must essentially weigh in on what is the rank your operational priorities for your business activities, and then accept what are the acceptable trade-offs in operational performance to avoid a strategic penalty layer. So we have, here are the issues we're going to look at: speed, reliability, security, and maintainability. These are operational. And then you have strategic, which is scalability and evolvability. So if you look at it, client-server architecture can be fast and reliable. None are inherently secure. Cloud computing is easier to maintain. Peer-to-peer is a lot more scalable, and none are inherently more evolvable. And the third layer we're going to look at is our data. So we talked about your basic IT architecture, then we looked at the application layer, and now we're going to look at the data architecture. Data architecture essentially focuses on one aspect: where is your firm's data stored? Integrated firm-wide data is the foundation of IT-enabled automation. However, the prevalent problem in firms is proliferation and duplication of and inconsistent data. This problem is caused because of dispersion of firms' data across applications and then across geographic regions. There are two solutions to it. One is to pick appropriate data architecture. Non-IT managers must decide on what data should be centralized firm-wide for executing your core business processes and for analytics, and what data must be shared across your markets. So when we talk about fragmentation of data, It's the consequence of applications in your firm's application portfolio. Remember that a firm's IT portfolio has many applications. Although most common cloud and client-server applications both centralize data, such centralization is usually for one application. Every application has its own centralized server, and their multitude can create silos of data scattered across different applications. Let's take an example of an online ordering app which will store its data on a different server for payroll or customer service app, and each one is separate. So similar data can therefore be duplicated across applications and be inconsistent over time. And this is the example of Delta Airlines' older system, which produced 17 different answers for a simple question about a flight's gate number. The dispersion in geographic region can also be a problem when the application's users become geographically dispersed. Although the app might begin with one central server that your employees or customers use, its operational performance can degrade to unacceptable levels if your colleagues in, let's say, Singapore has to constantly access data to do a day-to-day job with the machine sitting in Atlanta. You can choose between two solutions to solve this problem. Entirety of the firm's data for an app which you make multiple copies of, or you slice it into pieces and spread it around. The first approach is called replication, where you make copies of the entire data and keep a copy at each location so users' application can make quick local trips to access it. To ensure that copies remain synchronized, you connect them using the internet. Or you can slice up an application's database into smaller pieces where each piece keeps data only for the local area. By connecting each piece to the internet, you can slowly send and read data from far off locations or assemble copies on it in the database. So here is the example on replication, which I talked about, where you make copies of the data or you make slices of it, like cheesecake slices, and partition it. So in summary, IT architecture is the technology's DNA. It focuses and produces constraints on what your firm can do, and so you have to look at both of operational performance and then look at strategic evolvability in the future. More complex architecture causes brittleness, and so it is important to focus on simplicity of architecture that lowers complexity. IT architecture is essentially a bridge which is created between business people, the functional department, and the technology department to foster a shared purpose. We have enterprise architecture, which has three classes of IT assets in a portfolio. That's the infrastructure architecture, which centralizing lowers cost, but decentralizing might help it tailor it for diverse business needs. The application architecture of how the three building blocks are split across the internet. And finally, the data architecture that determines data consistency and accessibility. The key piece which you need to take from this particular chapter is, without functional managers' involvement, IT architecture is strategically blind. And so IT strategy must serve your overall corporate strategy, and therefore it's very important that functional managers are involved in this process.